Okay, let's continue. Now we are approaching what is proper mathematical physics. Namely, I start consider the string oscillations. No, string, it is what we see in guitar or in piano. It is a long thread, metal thread, or made of metal or some other material. When you displace its middle, it starts oscillating. Yeah, and the theory of this oscillating spring was, I think, the birthbed of the whole mathematical physics as we understand it today. So consider this string. It is the shape of string at some moment. Now, assume that the string is long, maybe infinitely long, so we consider it like a line in the coordinate system. This is x, this is say y, and the shape of the string is described by the equation y equals u of xt. X is the coordinate and t is the time. First thing. Second thing, what is the string materially? Materially, each piece of string has some mass, which is proportional to its length. Yes, so the mass m equals L times some rho. Rho is linear density of the string. So the mass of, say, 1 meter of the string. Rho, it is linear density. It is the mass of the string. Now, the string is stressed with some force. So if you take any point of the string, then the left part of the string pulls the right part with some force, and the right part pulls the left part with the same force. And the force is denoted by sigma. It is measured, say, in newtons. So stress sigma. So these are two parameters which are given from the beginning. It is part of the data of our problem. The stress and the linear density. Now we consider, one moment, we consider small oscillations of the string, so that the string is always close to the x-axis, and its, say, inclination, its derivative is also remains also small. Now, this condition is usually fulfilled in musical instruments like guitar or piano. No, sometimes it is far from reality, but we consider this case. So, suppose module u, module du dx are small. Small means in different situation means different. No, small as small as we need. Now the next thing is to derive the differential equation which describes the motion, means that this function u of xt satisfies some differential equation. And we, next step, I am going to derive this equation. So this string equation. Consider some piece of a string. For example, like this. This is a piece of a string between 2 points with coordinate x1 and x2. And consider the momentum of the string, of the piece of the string between these points. This part, it is material, it has some mass. Its mass equals the distance between x1 and x2 multiplied by linear distance. So it is some material mass. Yes? So momentum between x1 and x2, momentum, equals integral from x1 to x2 rho. And now what is the velocity of the string? It is ut, du dt. You know these notations, I'm sorry. Ut equals du dt, ux equals du dx, uxx equals d to u dx square, and so on. So these notations from calculus. Rho ut dx. Yes? No, if you want, of x. So it is momentum. Momentum depends on t, and of course depends on these points x1 and x2. This momentum. Now momentum is changed if some forces are applied to the body. Momentum of any body is changes under the influence of some forces, and the second Newton's law says that the rate of change of momentum is equal to the sum of applied forces. So which forces are applied? Here we have the forces are directed along the tangent to the string at the end point, here and here. Yes? So it is the force F1, and this is a force F2. It is vector forces. Yes? Now, this force has two components, horizontal component and vertical component. Horizontal component here and here is approximately the same, and anyway, if they are not the same, it results in small motions of the pieces of the string in the direction of x1 axis, which is not interesting for us, so we neglect them. The vertical component are the following. If here the vertical component is so F1. Okay, let me consider in more detail. This is vector F1 equals horizontal, first of all, sigma it is the modulus of this vector times cosine alpha sine alpha. Alpha is this angle which the force F1 or correspondingly F2 forms with the horizontal direction of the x-axis. So it is F1. Now what is cosine alpha? We know that tangents alpha equals ux. Derivative equals du dx. Yes? It's so this is tangents alpha. Now we know that sine alpha, for small alpha, I assume that this is small, is approximately equal alpha, approximately equal tangents alpha. Yes, up to higher order of alpha. And this means, cosine alpha is approximately equal 1, up to square terms of square of derivative. Again, with higher up to higher order terms. This means that F1 approximately equal 1. I'm sorry, sigma times 1 ux at the point x2, no, t, yeah, and f2 approximately equal sigma times minus 1 minus ux at the point x1 t. Yeah? So these two vectors. And so we can write the second Newton's law the following form. The time derivative of integral from x1 to x2 of what? ut xt dx equals one moment, rho equals sigma ux of x2 minus ux of x1. Ux of x2t minus ux of x1t. Yeah, no, instead of this approximately, I simply write simply equal because it is a tedious thing to estimate different small terms here. Let us swallow this, think that it is more or less equal. Yes? Now let us transform it a little bit. What is d dt of integral? These limits are constant, they don't depend on t, so we have to differentiate with respect to t this. So we differentiate ut, it is second derivative. So we write integral from x1 to x2 rho u tt dt. No, I drop this. It is here. It is time derivative of momentum of the string between the point x1 and x2. And here I make the following sigma. This difference between ux at this point and ux on this point, x1, x2 and x1, is integral from x1 to x2 of derivative. Yeah. Let me write integral from x1 to x2 sigma times u x, because let us find the derivative of ux and integrate it. We get the difference between ux here and here. Dx. I'm sorry, dx here also, of course. Or integral from x1 to x2. We have two integrals in the same limit, so we can join in one. Rho u tt minus sigma u xx dx equals 0. So it holds, I write, this holds for any t and any x1 and x2. No, I assume that x1 less than x2. So now let us consider this function. So what is written here? I everywhere have to add here of xt. Yes. So we have some function. Say k of xt. Yes. And of this function, we know that integral from x1 to x2 k of xt dx equals 0. Yes. So for any t x1 x2. We know that for some function, no, k is I denote this function by k of xt. Yeah, no, to denote it somehow. Let's denote it by k. So now suppose k of xt is a continuous function. The set of continuous function is denoted by c, continuous. Functions. Now we have the following situation. We have continuous function k. No, for given t, for any, let us do it for any fixed t. For any fixed t, we have a function k of x, t is parameter, and about this function it is known that this function, if you take any x1 and x2, integral from x1 to x2 k of x t dx equal 0. What can be said about this function? This is a great thing which is called, I think, du Bois-Reymond lemma, that from this follows then k of x t identically equals 0. So if the function is such that integral of this function along any segment is 0 and the function is continuous, then the function is identically 0. Now the proof is not so hard. Let me sketch the proof. So suppose k of xt is more than 0 for some x and t. Let me drop t. In fact, t is just parameter, k of x. If k of x is for some x 0, so kx0 more than 0, k of x0 equals c more than 0. One moment, let me make some space. Then by the definition of continuous function, then there exists epsilon such that k of x more than c over 2 for x0 minus epsilon less than x0 less than x0 plus epsilon. It is by definition of continuous function. Yes? Less or equal. And then integral from x0 minus epsilon to x0 plus epsilon k of x dx is more than c over 2 times epsilon, because the function is more than c over 2, the length of the segment is equal epsilon, c over 2 times 2 epsilon equals c times epsilon. Because the function is more than c over 2, the length of the segment is equal to epsilon, and the integral is more than c over 2 times 2 epsilon, which equals c times epsilon. Definitely it is more than 0. So we found a segment such that integral over this segment is more than 0. It is not 0. So this means that it is impossible to find a point where the function is positive. And the same is, we cannot find a point where the function is negative. So the same similarly, if k of x0 less than 0, then there exists epsilon, positive epsilon, such that k of x less than k equal minus c, k of x0 equals minus c, less than minus c over 2 for x0 minus epsilon less than x0 plus epsilon, and integral from x0 minus epsilon to x0 plus epsilon, k of x dx is less than minus c over 2 times 2 epsilon equals minus c epsilon, which is less than 0. So in both cases we have a contradiction. Now I tell you this reasoning in such detail because very soon we will need similar reasonings and similar properties, so it is necessary for us. Okay, so this means that this is true for every t, and so it is true for every x and t. So for every x and t, k of xt equals 0. Now let us recall what is k of xt. K of xt equals rho utt minus sigma uxx. Yes? So this is the function. And so we have the following great equation. Rho utt minus sigma uxx equals 0. Now we can divide by rho and have utt minus sigma over rho uxx equals 0. So this equation is called string equation. This is a string equation which describes the motion of a string. It works for infinite string and for finite string as well, because all our reasoning was within the segment where this function is defined, u of xt. It is a universal equation Here we have this coefficient sigma and rho, which are important for any practical problem, but for our theory we can set sigma and rho equal 1. No, it can be achieved by the choice of units, for example. Anyway, in the next practical session we will consider more realistic situation when sigma and rho are not 1, but as a model of our situation, consider the simplest case. Suppose sigma and rho equals 1, and so our equation becomes the following: u tt minus u xx is 0, or d2u dt square minus d2u dx square equals 0. So this is what can I say about this equation? This equation is an equation of second order, yeah, because it involves derivative of second order, partial derivatives of second order, and in what follows we will study mostly the second order equations, different second order equations which describe different basic physical processes. The next step is, after we derive this equation, the next step how to find its solution. We start this activity in the next lecture, and now let us finish for a while, and I wish you to have a good time in between. Bye.